attenuation, and propagation velocity. An interesting property of quartz is that it is possible to select the temperature dependence of the material by the cut angle and the wave propagation direction. With proper selection, the first order temperature effect can be minimized. On acoustic wave temperature sensors may be designed by maximizing this effect. This is not true of lithium niobate or lithium tantalate. Other materials with commercial potential include gallium arsenide, silicon carbide, langsite, zinc oxide, aluminum nitride, lead zirconium titrate. So whereas the acoustic wave devices are manufactured by means of photolithographic process similar to the use of make devices. The only difference is that no junction exists in acoustic wave sensors. A typical acoustic device which consists of two interdigital transducers. One transducer converts electric field into mechanical and other will be for the vice versa. When you are saying about an fabrications, so it is carefully by polishing and cleaning the piezo surface. The device is spin coated with photoresist and then it is exposed to UV light. The exposed areas undergoes a chemical change, then develops solution. Finally, the photoresist will be removed. The pattern of metal remaining on the device is called interdigital transducers. So by changing the length, width, position, and thickness of IDT, the performance of sensors can be maximized. When you are saying about an application, hydrogen, gas, pressure, and temperature, high temperature sensing, space applications, so ultra wideband communications, multi-sensor spectrum systems. So the next thing we are need to see about an radiation sensors. It works on the principle that as radiation passes through air or a specific gas, ionization of the molecules in the air occurs. By placing a very sensitive device between the wires from the cathode and anode, the small current is measured and displayed as signal. The radiation is energy traveling in the form of particles or waves in bundles of energy called photons. Some everyday examples are microwaves used to cook food, radio waves for radio and televisions, light and X-rays used in medicines. Radioactivity is a natural and spontaneous process by which the unstable atoms of an element emit or radiate excess energy in form of particles or waves. These emissions are collectively called ionizing radiations. Depending on how the nucleus processes this excess energy, either a lower energy atom of the same form will result, or a completely different nucleus and atoms can be formed. Ionization is the particular characteristics of the radiation produced when radioactive elements decay. These radiations are of such high energy that when they interact with materials, they can remove electrons from the atoms in the material. This effect is the reason why ionizing radiation is hazardous to health and provides the means by which radiations can be detected. So what about scintillation detector? The principle behind this instrument is the use of special material which glows or scintillates and radiation interacts with it. The most common type of material is the type of salt called sodium iodide. The light produced from the scintillation process is reflected through a clear window where it interacts with the device called photomultiplier tube. The first part is made up of one called photocathode. So the photocathode which produces electrons and light strikes. The electrons will then pull towards a series of plates called diodes through the application of positive high voltage. An electron from the photocathode hit the first diode. Several electrons are produced for each initial electrons hitting its surface. This bunch of electrons is then pulled towards the next diode, where more electron multiplication occurs. The sequence continues until the last diode is reached. The electron pulse is now millions of times larger than it was the beginning of the tube. At this point, the electrons are collected by an anode at the end of the tube, forming an electronic pulse. The pulse is then detected and displayed by the instrument. Whereas in the case of a gas field detector, principles as the radiation passes through air or specific gas ionization of molecules in the air occur. When a high voltage is placed between two areas of the gas filled space, the positive ions will be attracted to the negative side. So the free electrons will travel to the positive side. These charges are collected by the anode and cathode, which then form a very small current in the wire's coin detector. By placing a very sensitive current measuring device between the wires from the cathode and anode, the small current is measured and displayed as a signal. The more radiation which enters the chamber, the more current is displayed by the instrument. Many types of gas field detectors exist, but the two most common are to be the ion chamber used for measuring large amounts of radiation, or GM detector is used to measure very small amounts of radiation. Advantages and disadvantages and applications. So advantages, it is used for measurement in liquid and solid. It is used for continuous level measurement. It is simple in design and construction. External radiations may affect the measurement. Relatively expensive is a disadvantage. Applications, it is used in glass industry, steel industry, and petrochemical industry. So thank you all.